When a filament snaps on in a dark room, it releases radiant energy. This physical phenomenon allows the human eye to perceive objects around us. But simply generating light is not the same as engineering it. Illumination is the precise discipline of taking that raw radiant energy and mapping it onto physical surfaces where work actually gets done. If an electrician assumes that a bright bulb automatically equals a bright workbench, the results are dangerous. Miscalculating how light travels leads to severe inefficiencies, extreme eye fatigue, and catastrophic workplace accidents. To control a visual environment, we have to measure three distinct physical components. There is the source, like the bulb itself, the medium, such as the air or a glass cover, and the surface, which is the floor or desk receiving the light. By isolating and calculating the behavior of each of these three components, you can perfectly predict exactly how much light will reach a worker's hands, preventing fatigue and ensuring safety. The measurement process starts at the source. The total amount of light energy emitted by a bulb every second, radiating outward in every possible direction, is called luminous flux. This total omnidirectional output is measured in a unit called the lumen. Measuring light in all directions is rarely useful for practical engineering. In a workshop or an office, we generally only care about the light aimed directly at a specific target, like a machine or a desk. This diagram illustrates a three-dimensional cone projecting from the source, known as a solid angle, measured in steradians. Isolating the luminous flux within this specific cone gives us a new metric, luminous intensity, labeled I. This directional intensity is measured in units called candelas. While candelas give us the raw directional power of the source, they still do not tell us the actual density of usable light that successfully reaches the worker's hands. To find out what reaches the worker, we must shift our perspective away from the bulb and look down at the intersecting flat plane where human activity happens. Looking at this diagram, we see a downward beam striking the floor. The density of luminous flux striking exactly 1 square meter of this receiving surface is mathematically defined as illumination. The strict unit of measurement for surface illumination is the lux, which is equivalent to exactly 1 lumen per square meter. Lux is the exact metric read by light meters on the factory floor. It is the number used to determine if a workspace has enough light to be legally and physically safe to operate in. Delivering a specific lux value is the ultimate goal of lighting design. But lux is highly fragile, subject to severe degradation as the light travels through three-dimensional space. The first primary vulnerability of light is straight-line distance. A common intuitive assumption is that if you double the distance from a light source, the brightness simply drops by half. That assumption is mathematically incorrect and highly dangerous in an industrial setting. The decay of light follows the inverse square law. This diagram shows a pyramid of light from a single point. At distance d, light fills a single square, area A. As the beam travels downward, the exact same energy stretches across a wider space. By doubling the distance from the source to 2d, light spreads over 4 times the original area. Because energy is diluted across 4 squares, illumination intensity drops to 25%. Simply moving a work surface slightly further from a fixture results in a massive, non-linear collapse in usable lux. This exponential decay demands exact precision when calculating the height placement for all industrial lamps. The second major vulnerability of light is the angle of incidence. Here, a light beam strikes a horizontal surface perfectly straight down, achieving maximum intensity at a perpendicular 90-degree angle, called the normal. Watch as the surface tilts. An angle forms between the normal line and the incoming slanted light. The total lumens hasn't changed, but because the energy is smeared across a larger, stretched oval, the lux drops significantly. This is Lambert's cosine law. Surface illumination is directly proportional to the cosine of the angle, theta. Even if the distance to the bulb remains totally constant, a slight tilt in a drafting table or a misaligned spotlight fixture will silently bleed away critical lux from the workspace. We can observe both of these geometric laws interacting in a universally recognized scenario, walking down a dark road under a single overhead street lamp. This diagram illustrates a person standing dead center beneath the lamp. At this exact position, the visual UI shows a high lux reading at their feet. This is the peak moment of illumination. The straight line distance is at its absolute minimum, and the angle to the normal is exactly 0, so the lux is maxed out. Now observe as the person takes 5 steps forward. The UI updates in real time. The distance line stretches, the angle widens, and the lux reading plummets rapidly. The inverse square law is now actively degrading the light, because the physical distance from the bulb to the feet is increasing with every step. Simultaneously, Lambert's cosine law is also degrading the light, as the beam from the street lamp is now striking the ground at a severe slant. This dual decay, an exponential loss of light over distance, multiplied by a wider angular spread, is the exact mathematical reason why shadows stretch dramatically and visibility drops to near 0 just a few yards outside the light cone. In industrial maintenance, these physical laws become actionable troubleshooting steps. When a worker reports dim lighting and a lux meter confirms a low reading, the electrician must trace the physics backward to find the fault. The spatial techs come first. The electrician verifies if the machinery has been moved further away, triggering an inverse square fault, or if the fixture angle has vibrated out of alignment, creating a cosine fault. Next are the source checks. The electrician inspects the fixture for broken incandescent filaments or loose wiring connections that cause rapid, physical flickering in the intensity of the light. Finally, the transmission medium must be checked. In factories, heavy granular pollutants and dust frequently settle thickly over the glass housing of the fixtures. Even if the bulb's luminous flux in lumens is completely flawless, an obstructed medium chokes the luminous intensity in candelas before the light can ever leave the source. The standard protocol for restoring the system addresses each point of failure, securing loose electrical connections, strictly maintaining specific fixture angles, and routinely clearing the transmission medium. Proper lighting design is rarely solved by simply installing a higher wattage bulb to overpower a flawed setup. True illumination control is the complete mastery of geometric physics. By mathematically manipulating radiant energy, distance, and angles, an electrician guarantees a visually precise, highly productive, and physically safe human environment.